तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we acquainted ourselves with the concept of the state of a system, what is meant by state variables, and the nature of the equations connecting the state variables with the input and output quantities. We worked out an example where the state equations are formed. When I say state equations, I mean the state equation and the output equation put together, and we used an ad hoc approach in writing down the state equations pertaining to that example. There are streamlined methods of doing this. One which uses topological methods, graph theoretical concepts, and gives a systematic way of writing the state and output equations in matrix form, taking the various network circuit parameters into consideration. We will not deal with that, but we will take up another fairly general method which works reasonably well in networks of moderate complexity. I will first demonstrate this through an example and then discuss the general steps that are involved in adopting this procedure. Let us consider a network like this containing an inductor, a resistor, and a capacitor, and there are three sources, E1, E2 voltage sources and a current source Is. So this example have various representative elements, one resistor, one inductor, one capacitor, two voltage sources and one current source. So the input quantities are E1, E2 and Is, time varying quantities. They are the sources, and we desire to find the solution for I1 and I2. So I1 and I2 are the output quantities, are the responses. So we straight away see that the U matrix, that the input quantities are E1, E2 and Is. The output quantities are I1 and I2. So Y, we will write capital U and capital Y as I1 and I2. As I mentioned in the last lecture, it is convenient to take the inductor current and the capacitor voltage as state variables in a system like this. Therefore, the state variables are IL and VC. I will take VC first and then IL. Therefore, let me put this VC and IL as the state variables. These are the state variables. So that is a natural choice. Now we would like to express x dot in terms of x and u, because after all you have to write x dot equals ax plus bu. And what is x dot? X dot is Vc dot and IL dot. So the current in the capacitor is CVC dot. So we have to express the current in the capacitor in terms of the state variables and the input quantities. Similarly, IL dot, the derivative of the current in the inductor, is related to the voltage across the inductor. VL is L dIL by dt. Therefore, we have to express the voltage across the inductor and the current to the capacitor in terms of IL, VC, E1, E2 and Is. So to do this, it will be convenient for us to write down the equations if we replace Vc, the capacitor, by a voltage source equal to Vc and the inductor by a current source of value IL. Let us do that. So I have Is here, and the inductor is replaced by a current source IL, and the capacitor is replaced by a voltage source Vc, and then you have resistance R and you have the other sources E1 and E2. And we have to find out the voltage across the inductor, that is VL, so we will call this VL, and the current through the capacitor I would like to call that IC. So that is the current here IC, and the voltage across the inductor is VL. So this is what we are interested in finding out. It is only a convenient representation by representing a inductor by a current source and a capacitor by a voltage source. You do not have to do it. If you can write down the equations for VL and IC in terms of IL, VC, E1, E2 and IS in any other manner, it is possible. But what we want to do is emphasize that we have to express this voltage and this current in terms of various sources and the non-dynamic elements that are involved there, the resistance. That is what we are interested in. Therefore, it is convenient for us to replace it by these sources, because it will bring into focus that we have to express the response quantities in the circuit due to the various sources and also in terms of IL and VC. So that we have to express this in terms of IL and VC. So if IL and VC are made sources, it becomes very convenient for us to do so. So in this network, we have to find VL and IC in terms of IS, IL, VC, E1 and E2. So we have several sources now. Really there are 5 sources, and we have to find out 2 response quantities VL and IC. You can solve this network any manner you like. You can use the principle of superposition, take one source at a time and find out the contribution of that each source to VL, to IC, and add them up. Otherwise, if you have any other method, you can find out the solution in one shot. Whatever might be, you can show that VL equals, solving this network, through superposition or otherwise, I will write that. There is no compulsion on our part that you should do only superposition, it can be any other method. VL turns out to be, VL of course is no L IL dt, that we know. This turns out to be E1 minus E2 minus VC. That you can see from this loop. VL equals E1 minus E2 minus VC. So we have got an equation for IL dot. Similarly, IC, the current which is CVC dot, the current here is C times VC dot, can be shown to be minus E2 by R plus IL minus VC by R. So from these 2 equations we can get IL dot and VC dot by dividing right through by L in the first equation and C by the other equation. So we have 2 expressions for IL dot and VC dot, the derivative of the state vector in terms of E1, E2, VC and IL. E1, E2 are the input quantities, and VC and IL of course are state variables. So we have final result. Therefore, using this you can write, from this you can write VC dot IL dot, this is X dot really, is a matrix minus 1 over RC, 1 over C, minus 1 over L, 0, multiplying VC and IL. This is the matrix A, this is the matrix X, plus BU. U is the input vector which have 3 quantities, E1, E2 and IS. So we have to write E1, E2 and IS. And we have 3 columns here therefore, and that would turn out to be 0, minus 1 by RC, 0, 1 by L, minus 1 by L and 0. That is plus B. So X dot equals AX plus BU, that equation has been established. Now we have to find out the output quantities. Output quantities are I1 and I2. We have to express that in terms of the state variables and the input quantities. We note that I1 equals IL plus IS. So that is straightforward, and similarly we can express I2 in terms of E2, E1, IS and IL. So I will write these equations first. I1 equals IS plus IL and I2 equals, it can be shown from the circuit diagram, E2 by R minus IS minus IL plus VC by R. So you can put this in matrix form as I1 I2 equals, in terms of the state variables VC and IL, and that will be 0 1 1 by R minus 1 plus E1 E2 IS, and the three corresponding entries here 0 0 1. You see I1 equals IS plus IL, I1 equals IL plus IS. So other entries will be 0, and I2 equals E2 by R. Therefore I will get 1 by R here, E2 by R, minus IS, therefore I have a minus 1 sign here, minus IL plus VC by R, that has already been completed. So the second equation represents Y equals CX plus DU. So that is the standard form of the equation, Y equals CX plus DU. So this is what we do to establish the state and output equations starting from the given configuration. So let me just review the steps that are involved. What we do is, you have, suppose you have a general network in which you have various voltage sources. So suppose say VSK, so a number of voltage sources, and a number of current sources ISK, and you have various capacitors. Suppose this is CK, and then you have VCK as the voltage across that, and you have various inductances LK, the current through that is ILK. So you bring the reactive elements and the sources separately as the exhibit, and whatever is left inside is the non-dynamic portion. Non-dynamic part. It may be purely resistive network, or it may also have dependent sources which are non-dynamic in character. So what we are trying to do is, you replace this the capacitors and inductors by voltage source and current sources. So that means what you are doing now is, you are replacing this by a voltage source VCK, and the current and the inductor is replaced by current source ILK, and the others are as before. This is VSK, this is ISK. At this stage we have a non-dynamic network acted upon by various sources. So you find out the current ICK in this and the voltage VLK in this. So you express VCK and ILK for various Ks, that is various capacitors and inductors, in terms of VSK, ISK, ILK and VCK. ILK and VCK, that set constitute the state variables. ISK, this ISK and then VSK constitute the input quantities. So you found ICK and VLK, which are in turn, after all ICK is CK times VCK dot, and VLK is LK times ILK dot. So in other words, you have found out VCK dot and ILK dot for various values of K in terms of VCK, ILK, which constitute the state variables, and VSK and ISK, which constitute the input quantities. So first step is to replace this by sources. Second step is to find out the currents in the replacement voltage sources and the voltages across the replacement current sources, and identify them with as proportional to the derivatives of the state variables. So you have got the derivatives of the state variables expressed as a function of the state variables themselves and the input functions plus the network parameters, which are R, L and C. In the same fashion, in the same network here, you can express the output quantities that you are interested in terms of Vsk, Isk, Vck and Ilk, which are the state variables. So in analyzing this, you already can find out the equations for the output quantities in terms of the state variables and the input quantities. So we have on one hand the state equation and then also the output equation. So this is a general procedure. It is a straightforward extension of what we have done. It is the best. The example illustrates actually the steps that are involved. What we have done is we put this in a more general framework, where K can be a running index depending upon the number of inductors, capacitors and voltage source and current sources. What we have discussed so far is the normal form of state and output equations. X dot equals Ax plus Bu and Y equals Cx plus Du. It turns out that in special situations we have to deviate from the normal form of the state and output equations. Such cases arise where you have loops constituted by capacitors and voltage sources and cut sets constituted by inductors and current sources, where the number of state variables will be reduced from the total number of reactive elements by the number of independent CVS loops or LIS cut sets. So in these special cases we will have what is called an extended form of the state and output equations, and that I would like to discuss now, illustrating this by through an example once again. So special case where CVS loops are present. By this what I mean is that you have a closed circuit constituted entirely by capacitances with or without voltage sources. That is, if the loop, all the elements inside the loop must be either all capacitors or some capacitors and some voltage sources. In such cases we have the extended form of these equations. The extended form will be X dot equals Ax plus Bu as before. In addition, you have another matrix E multiplying U dot, where U dot is the vector of derivatives of the input functions, and Y likewise is Cx plus Du, this is the standard form, plus F times U dot. So these new matrices E and F arise whenever you have CVS loops, or we will first talk about with this and also we will say that similar cases arise when inductor, current source, cut sets are present. So let me as well put here and LIS cut sets are present. So even in this case we have this extended form. How these extended forms arise will be illustrated by means of an example. Let us consider that we have a circuit in which two sources are acting. We have three resistors and three capacitors like this. So let this be C1, this is C2 and this is C3, and this be R1, R2 and R3. To simplify numerical work, let us take C1 equals C2 equals C3 equals 1 farad and R1 equals R2 equals R3 equals 1 ohm. Now we observe that the three capacitors and the two sources form a loop. Consequently, the sum of the capacitor voltages and the source strengths must add up to 0 according to Kirchhoff's voltage law, which means that these three capacitor voltages cannot be all independent. Therefore, one of them depends on the other two and the source voltages. So we can straight away observe, note that all three capacitor voltages cannot be state variables. Consequently, let us take Vc1 and Vc2, Vc1 and Vc2 as the state variables, and the voltage Vc3 depends on Vc1 and Vc2. So, if you write the Kirchhoff's voltage law for this loop, you will observe that E1 plus E2 equals Vc1 plus minus Vc1 plus Vc3 minus Vc2, or in other words Vc3 equals E1 plus E2 plus Vc2 minus Vc1. So, Vc3 depends on the other, Vc3 depends upon E1 plus E2 plus Vc2 minus Vc1. That is what we are having. So, in this what we do is to set up the state equations pertaining to this, we replace C1 and C2 by voltage sources of strengths Vc1 and Vc2 according to our usual method. However, as far as this capacitor is concerned, which we will refer to as excess capacitor, because in this loop this is an excess capacitor, that will be replaced not by a voltage source, but let us say that we replace it by a current source which is IC3. So, the state vector now is Vc1 and Vc2 is the state vector, and IC3 is the current in the third capacitor, which we will take to be an excess capacitor. That is the C3 will be an excess capacitor, and that will be replaced by a current source of strength IC3. We will see how to handle that. Let us imagine that we are interested at the output quantities, the two currents I1 and I2. I1 and I2 are the output quantities. So, we have now the state vector is Vc1 and Vc2, and the output quantity or output vector is I1 and I2. I1 and I2, that is what we have as the output quantity. Now, so to analyze this, what we do according to our usual practice, we have E1, E2, and this voltage, this capacitor is replaced by a voltage source of strength Vc1. The second capacitor is replaced by a voltage of strength Vc2, and we have R1, R2 and R3 all of unit magnitude, and the third capacitor now is replaced by a current source of strength IC3. Now, we have to find out IC1 and IC2 in terms of the state variables Vc1, Vc2, E1, E2, and also a new fictitious source that we have introduced here, IC3. So, we express IC1 and IC2 in terms of Vc1, Vc2, E1, E2 and IC3 in the usual fashion, and if you analyze this, you will find that IC1 equals 2/3 of E1 minus Vc1 plus 1/3 of E2 plus Vc2 plus IC3, and likewise IC2 can be shown to be minus 1/3 of E1 minus Vc1 minus 2/3 of E2 plus Vc2 minus IC3. So, let us call this equation A, let this be equation B. Now, we have, of course, IC1 is C1 times Vc1 dot and IC2 is C2 times Vc dot. So, this is according to what we have, except that now we have a new quantity which we would like to get rid of. IC3 is an extraneous quantity which we should like to get rid of. But you notice IC3 is equal to C3 times Vc3 dot, and we know Vc3 dot equals E1 plus E2 plus Vc2 minus Vc1. Therefore, IC3 can be written as C3 times Vc3 dot, which is the but C3 is equal to 1, therefore this is Vc3 dot, and from this you get this as E1 dot plus E2 dot, where dot is the derivative, plus Vc2 dot minus Vc1 dot. So this is third equation C. So this equation C will enable us to express IC3 in terms of the derivatives of the sources and the derivatives of the state variables. So if you substitute the third equation into the first two equations, then we can get rid of IC3 and you have an equation which concerns Vc1 dot and Vc2 dot in terms of the state variables and the derivatives and the source functions and their derivatives. So you work this out, from ABC we can obtain Vc1 dot, Vc2 dot, the derivative of the state vector equals minus 1/3, 0, 0, minus 1/3, Vc1, Vc2 plus 1/3, 0, 0, minus 1/3, E1, E2 plus a new matrix that we have got 1/3, 1/3, minus 1/3, minus 1/3, E1 dot, E2 dot. So this is the E matrix that we are getting now. That is the new one that we have got now. The output quantities, we want the I1 and I2 are the output quantities. We know I1 equals the same as IC1 and I2 equals the negative of IC2. Therefore, we already have an expression for IC1 and IC2. Therefore, from that you can get I1 and I2. That's quite easy to obtain. Therefore, you have I1 and I2 equals minus 1/3, 0, 0, 1/3 of Vc1, Vc2 plus 1/3, 0, 0, 1/3 of E1, E2 plus 1/3, 1/3, 1/3, 1/3 of E1 dot, E2 dot. So that's how you can obtain the extended form of the state and output equations once you have source and capacitor loops. So all the principle that is involved is that you have the excess capacitors are replaced by current sources, and you write the equations in terms of the source strengths, state variables and the additional current sources, and the current sources are eliminated by writing out an extra equation for the current source strength in terms of the derivative of the excess capacitor voltage, which in turn can be expressed in terms of the sources and the other capacitor voltages. And whatever we have done can be extended for the wherever inductors and current sources form a cut set. Even in that case, what we have to do is the excess inductors can be replaced by a voltage source, and then you write the expression for the current in that excess inductor, of course, is related to the currents in the regular inductors whose currents are associated as state variables and the current source strengths, and you take the derivative of the current in the excess inductor, and that will be the voltage across the excess inductor, and that can be expressed in terms of the derivatives of the state variables, the inductor currents which are state variables, and this current sources, and we, following the same analysis, will be able to write down the extended form as state and output equations wherever there are inductors and current sources form a cut set. The whole analysis follows an analogous lines to this. After learning how to write the state and output equations, it is now appropriate for us at this time to discuss ways of solving these equations. So essentially we solve for the state vector from the state equation x dot equals ax plus bu. So you solve for the state vector as a function of time. That means each component is known, each state variable is known as a function of time. This constitutes the most difficult part. After having found out the state vector, you substitute that in the second equation, this is the output equation, y equals Ex plus du. So it's a mere substitution and then carrying out the necessary algebra, and then you get the various components of y as functions of time, and that constitutes the complete solution. Before we discuss the methods of solution of the state equations, let me just dispose of one small matter, because we saw that the state equations can come in the standard form or the extended form. However, we don't have to discuss the extended form of the state equations, because through a suitable transformation we can transform the extended form of state equations into the standard form. I will just illustrate that, how the extended form can be converted into standard form through appropriate identification of new state variables, and then we will discuss the procedures of solving the standard form of state equations. So we will say solution of extended form can be converted to the solution of standard form. How? Let the extended form be x dot equals ax plus bu plus e times u dot, y equals cx plus du plus f u dot. So these are the extended form of equations. Now you define a new set of state variables xn as x minus eu. So this is a new set of state variables. Which are related to the old state vector by x minus eu. So this new set of state variables not only are dependent on the old state variables, but also the source function here. Consequently, you can write x dot equals xn dot equals xn dot plus e times u dot. Right? So you can substitute for x dot as xn dot plus eu dash in this, and you can simplify. You will finally get, you can show that using this relation, you can finally show that xn dot equals axn plus b plus ae times u, and y equals cxn plus ce plus d u plus f times u dot. Now, as I said, it is the solution of the state equation which is most fundamental, which is the more difficult, and now this is the new state equation which has to be solved for. Essential solution has something to do with A. So instead of the B matrix, you have B plus AE, a new matrix, but otherwise the form of this is the same as the old form in the standard form AX plus BU. So the whatever solution methods you have contemplate for the solution of x dot is equal to ax plus bu can be applied as well here. And once we have got the new state vector solution for the new state vector xn, you substitute here, and here there is a u dot, does not really matter because here you are only substituting xn and then calculating the value of y. You are not solving this as a matrix equation or whatever it is. It is a mere substitution and evaluating y. So you know the source function u, you can find out u dot, there is no difficulty, and therefore you can get the output y. So here afterwards, therefore we need not give any special mention or special illustrations of the solution of the extended form of state equations, because if you know how to solve the standard set of state equations, you can as well apply the same techniques for the extended case also by converting the old state vector into a new state vector with this kind of substitution. Okay. Now let us discuss the solution methods themselves. The solution of the state and output equations can be done in time domain, but before that we would like to use the Laplace transform techniques and find out the solution, because it will be illustrative and it will also give us some feel for the problem, because we already are familiar with the Laplace transformation techniques. We know what is the natural response, what is the forced response in the Laplace transform techniques, and see how this is related to the Laplace transform solution. And then later on we will talk about time domain solution where Laplace transformation technique is not at all used. So the first method of solution that we talk about is the Laplace transform method. What we mean by this is the coupled first order differential equations x dot equals ax plus bu will be solved by the Laplace transform technique. So we have x dot, a vector, equals ax plus bu. Recall that x dot is a vector, a number of variables, x is also a vector and u is also a vector. Take the Laplace transform of this equation. Of this entire set of equations. So after all, when you want to take the Laplace transform of x dot, okay, before that let the Laplace transform of x, what we mean by Laplace transform of x is Laplace transform of various quantities x1 up to xn. Let this be called xs. So it is a new vector where instead of the time dependent quantities, time variable quantities, we have transforms, functions of s. So Laplace transform of the x vector, let it be called xs. Now what will be the Laplace transform of x dot? You are taking the Laplace transform of x1 dot, x2 dot, xn dot. So if x1 has the Laplace transform of x1 of s, the Laplace transform of x1 dot is s times x1 of s minus x1 0. In line with what we do in the differential equations, we take the initial conditions pertaining to 0 plus. Therefore we get Laplace transform of x dot will be x1s minus x1 0 plus, like that it goes on. So I can write this entire thing s times x1 of s, I'm sorry, because we are taking the, if Laplace transform of x1 is x1 of s, Laplace transform of x1 dot will be s times x1 of s minus x1 0 plus, like that it goes on. So this entire vector, which consists of s times x1 of s minus x1 0 plus, s times x2 of s minus x2 0 plus, and so on and so forth, can be written as s times xs, because after all if there is a vector which is multiplied by a scalar s, every one of these components is multiplied by s, minus x0 plus, this is a vector of initial values. This is a vector of initial values. That is the value of the state at time t equals 0 plus. x is the state vector as a function of time, x0 plus is the state vector at time t equals 0 plus. So we have the Laplace transform of x as x of s, the Laplace transform of x dot is s xs minus x0 plus, all are n vectors, and the Laplace transform of u, we will call that u of s. After all, that is also a vector. So this entire set of equations can, in time domain, in the transform domain will look like s times x of s minus x0 plus equals a times x of s plus b times u of s. So this is the transformed set of equations. Transformed equations. Now what we are really having here is x1 of s is multiplied by s, x2 of s is multiplied by s. So here, in order, we would like to have x of s term here and x of s term here, we would like to combine these two. We have x of s there and x of s here, we would like to combine them suitably. Here it is multiplied by a matrix A, here it is multiplied by a scalar s. So to overcome this problem, after all, if I multiply these all zeros, x1 of s down the line to xn of s, if I multiply this, the vector x1 to xn of s by a matrix which has s right along the diagonal, this will of course be s times x1 of s, s times x2 of s, and so on and so forth, s times xn of s. And this particular matrix can be written, after all, we have, instead of, we have only diagonal entries and all of them are is equal to s, and this matrix is s times the unit matrix I, where I is the unit matrix. The unit matrix which has ones all along the diagonals. You find in literature unit matrix is also indicated as U, but since we are using U for something else, we use I. Unit matrix, that is a matrix which has got ones all along the diagonal, and to further say that it is a unit matrix of dimension n, sometimes people write In, but we will simply write I, because after all we are not writing the dimensions for the other quantities as well. Therefore this is s times In gives you this quantity, and that is exactly sxs. This is sxs. This is what we have here. So what I would like to do is, I will write this equation as s times I times xs minus x0 plus equals axs plus bus, and this matrix has a dimension n by n, and so is this matrix. So if you transfer this to the other side, I can write this as si minus a times x of s equals x0 plus bus. That is what you are having. Si minus a times x of s is x0 plus bus. This is now a matrix of dimension n by n. So this is a square matrix of dimension n by n, and we have to solve for x of s. So you can think of multiplying this entire set by the inverse of this matrix. We will assume that it exists, and then we got the solution for x of s. Therefore I can write x of s as si minus a inverse multiplying x0 plus the initial vector source, initial state vector, times si minus a inverse b times us. So that is the solution for the Laplace transform of the state vector in terms of the initial state x0 plus and the Laplace transform of the forcing functions u. Therefore in this solution, what is involved is the inversion of a n by n matrix, where n by n matrix is not a constant, it is also a function of s. Okay. Once we have that, then Once we have that done, we can find out the output quantity. After all, output equals, this is the state equation, output y equals Cx plus du. Therefore, taking the Laplace transform of this becomes y of s, the Laplace transform of the output quantities is C times x of s plus d times u of s. We know the solution for x of s from here. Therefore, we now have the final solution for the output in the Laplace transform domain as y of s equals C times Si minus A inverse x0 plus C times Si minus A inverse B plus D times u of s. So we have y of s in two parts, one which depends upon the initial state x0 plus and the other which depends on the forcing function u of s. That's what we are having. So y of s can be put in this form, C times Si minus A inverse times x0 plus C times Si minus A inverse plus B plus D. Suppose we have initial conditions 0. We assume that the capacitor and inductor currents are initially at 0 level and they don't change suddenly. That means, and you are applying an input, therefore this becomes 0 and y of s is equal to this times u of s. So what we can say is this part of the solution is obtained when the initial conditions are 0. That means the initial state of the system is 0. So this is called the 0 state solution. 0 state solution. What it means is the initial conditions are 0. That means the initial state of the system is 0. All the state variables are at 0 values. This portion will be is a solution. Suppose the input is 0. You have given some initial conditions to the system and let the system go on its own. Then the input is 0. Therefore, this whole thing becomes 0 and you have only this. So this is called the 0 input solution. So we have the solution, we consider this in two parts. One is the 0 input solution which arises when the input is 0 and the system is going on its own under the influence of the initial conditions. The second part is the one that would be obtained if the initial conditions were 0, which means the initial state of the system was 0, so it is 0 state solution. We have to find out the inverse Laplace transform of these quantities to get the output yt. You recall that this is a matrix equation. So ys will be, whatever we are getting here, will be a vector of functions of s, both in this term and this term. So to find out the inverse Laplace transform, we have to find out inverse Laplace transform of each one of those quantities. That's what we are having. Now we will talk about this in greater detail in the next lecture, because to find out Si minus A inverse and related aspects, it will take some time. But what we can see is, suppose you have a single input, single output system. There is only one input and one output. That means y of s is a scalar and u of s is a scalar, just one quantity. And the initial conditions are 0. Therefore, the Laplace transform of the output to the Laplace transform of the input is just this quantity. So in the case of a single output, single input system, the Laplace transform of the output to the Laplace transform of the input with 0 initial conditions is equal to this. Therefore, we can observe straight away that special case, single input, single output system, we have ys over us, 0 initial conditions, is our system function hfs, and the system function happens to be equal to this. So that system function C times Si minus A inverse B times D. So hfs is equal to C times Si minus A inverse times B plus D. So we have found out an alternative way of finding out HFS in terms of the ABCD matrices. So in this lecture we continued our discussion of the state variable concepts. In the last lecture we learned the concept of state and the number of state variables that come about in a particular network. Today we learned how to write the state and output equations. We discussed one general method where the capacitors are replaced by voltage sources and the inductors are replaced by current sources, and then we write the equations of performance of the resulting non-dynamic network excited by various sources and use that information to find state and output equations. We also saw the extended form of state and output equations when CVS loops are present or L current source cut sets are present. We said that it is not necessary for us to consider separately the method of solution of the extended form of equations, because the extended form of equations can be converted into the standard form through a suitable transformation of the state variable state vector. Then we started discussion of the Laplace transform method of solution of state equations, and we saw that the suitable Laplace transformation of the various quantities, we arrive at a solution for the state vector in this form in the Laplace transform domain and for the output vector in this form, and we said the output solution can be considered to be two parts, one which arises when the input is 0 input solution, and the other where the initial state is 0, this is called the 0 state solution. These two have special significance, as we will see later on in our next lecture. We will continue this discussion at this point in our next lecture.